A gear or cogwheel is a rotating machine part having cut teeth, or cogs, which mesh with another toothed part to transmit torque, in most cases with teeth on the one gear being of identical shape, and often also with that shape on the other gear. Two or more gears working in a sequence are called a gear train or, in many cases, a transmission. Such gear arrangements can produce a mechanical advantage through a gear ratio and thus may be considered a simple machine. Gear devices can change the speed, torque, and direction of a power source. The most common situation is for a gear to mesh with another gear. However, a gear can also mesh with a non-rotating toothed part, called a rack, thereby producing translation instead of rotation. The gears in a transmission are analogous to the wheels in a crossed belt pulley system. An advantage of gears is that the teeth of a gear prevent slippage. When two gears mesh, and one gear is bigger than the other, a mechanical advantage is produced, with the rotational speeds and the torques of the two gears differing in an inverse relationship. In transmissions with multiple gear ratios, such as bicycles, motorcycles, and cars, the term gear, as in first gear, refers to a gear ratio rather than an actual physical gear. The term describes similar devices, even when the gear ratio is continuous rather than discrete, or when the device does not actually contain gears, as in a continuously variable transmission. History. Early examples of gears date from the 4th century BCE in China, which have been preserved at the Luoyang Museum of Henan Province, China. The earliest gears in Europe were circa CE 50 by Hero of Alexandria, but they can be traced back to the Greek mechanics of the Alexandrian school in the 3rd century BC and were greatly developed by the Greek polymath Archimedes. Examples of further development include: Marjan used gears as part of a south-pointing chariot. The Antikythera mechanism is an example of a very early and intricate gear device, designed to calculate astronomical positions. Its time of construction is now estimated between 150 and 100 BCE. The water-powered grain mill, the water-powered sawmill, fulling mill, and other applications of watermill often used gears. The first mechanical clocks were built in CE 725. The 1386 Salisbury Cathedral clock may be the world's oldest working mechanical clock. Comparison with drive mechanisms. The definite velocity ratio that teeth give gears provides an advantage over other drives in precision machines such as watches that depend upon an exact velocity ratio. In cases where driver and follower are proximal, gears also have an advantage over other drives in the reduced number of parts required. The downside is that gears are more expensive to manufacture, and their lubrication requirements may impose a higher operating cost per hour. Nomenclature. General nomenclature: rotational frequency, n measured in rotation over time, such as RPM. Angular frequency, omega measured in radians, second. Rad, second number of teeth, n how many teeth a gear has, an integer. In the case of worms, it is the number of thread starts that the worm has. Gear, wheel, the larger of two interacting gears or a gear on its own. Pinion, the smaller of two interacting gears. Path of contact, path followed by the point of contact between two meshing gear teeth. Line of action, pressure line, line along which the force between two meshing gear teeth is directed. It has the same direction as the force vector. In general, the line of action changes from moment to moment during the period of engagement of a pair of teeth. For involute gears, however, the tooth-to-tooth force is always directed along the same line, that is, the line of action is constant. This implies that for involute gears the path of contact is also a straight line, coincident with the line of action, as is indeed the case. Axis of revolution of the gear, center line of the shaft. Pitch point where the line of action crosses a line joining the two gear axes. Pitch circle, pitch line, circle centered on and perpendicular to the axis, and passing through the pitch point. a predefined diametral position on the gear where the circular tooth thickness, pressure angle and helix angles are defined. Pitch diameter, d. A predefined diametral position on the gear where the circular tooth thickness, pressure angle and helix angles are defined. The standard pitch diameter is a basic dimension and cannot be measured, but is a location where the measurements are made. Its value is based on the number of teeth, the normal module, and the helix angle. It is calculated as in metric units or in imperial units. Module or modulus, m. Since it is impractical to calculate circular pitch with irrational numbers, mechanical engineers usually use a scaling factor that replaces it with a regular value instead. This is known as the module or modulus of the wheel and is simply defined as where m is the module and p the circular pitch. The units of module are customarily millimeters. An English module is sometimes used with the units of inches. When the diametral pitch, dp, is in English units, in conventional metric units, the distance between the two axes becomes where a is the axis distance, z1 and z2 are the number of cogs for each of the two wheels. These numbers is often chosen among primes to create an even contact between every cog of both wheels, and thereby avoid unnecessary wear and damage. An even uniform gear wear is achieved by ensuring the tooth counts of the two gears meshing together are relatively prime to each other. This occurs when the greatest common divisor of each gear tooth count equals 1, e.g., GCD equals 1. If a 1-to-1 gear ratio is desired, a relatively prime gear may be inserted in between the two gears. This maintains the 1-to-1 ratio but reverses the gear direction. A second relatively prime gear could also be inserted to restore the original rotational direction while maintaining uniform wear, with all four gears in this case. Mechanic engineers, at least in continental Europe, use the module instead of circular pitch. The module, just like the circular pitch, can be used for all types of cogs, not just evolvent-based straight cogs. Operating pitch diameters determined from the number of teeth and the center distance at which gears operate. Example for pinion. Pitch surface in cylindrical gears. Cylinder formed by projecting a pitch circle in the axial direction. More generally, the surface formed by the sum of all the pitch circles as one moves along the axis. For bevel gears it is a cone. Angle of action, angle with vertex at the gear center, one leg on the point where mating teeth first make contact, the other leg on the point where they disengage. Arc of action, segment of a pitch circle subtended by the angle of action. Pressure angle, the complement of the angle between the direction that the teeth exert force on each other, and the line joining the centers of the two gears. For involute gears, the teeth always exert force along the line of action, which, for involute gears, is a straight line, and thus, for involute gears, the pressure angle is constant. Outside diameter of the gear, measured from the tops of the teeth. Root diameter of the gear, measured at the base of the tooth. Addendum, a radial distance from the pitch surface to the outermost point of the tooth. Dedendum, b. radial distance from the depth of the tooth trough to the pitch surface. Hole depth, the distance from the top of the tooth to the root. It is equal to addendum plus dedendum, or to working depth plus clearance. Clearance distance between the root circle of a gear and the addendum circle of its mate. Working depth of engagement of two gears, that is, the sum of their operating addendums. Circular pitch, p. distance from one face of a tooth to the corresponding face of an adjacent tooth on the same gear, measured along the pitch circle. Diametral pitch, dp. ratio of the number of teeth to the pitch diameter, could be measured in teeth per inch or teeth per centimeter, but conventionally has units of per inch of diameter, where the module, m, is in metric units. In English units, base circle in involute gears, where the tooth profile is the involute of the base circle. The radius of the base circle is somewhat smaller than that of the pitch circle. Base pitch, normal pitch, in involute gears, Distance from one face of a tooth to the corresponding face of an adjacent tooth on the same gear, measured along the base circle. Interference contact between teeth other than at the intended parts of their surfaces. Interchangeable set of gears, any of which mates properly with any other helical gear. Nomenclature. Helix angle between a tangent to the helix and the gear axis. It is 0 in the limiting case of a spur gear, albeit it can be considered as the hypotenuse angle as well. Normal circular pitch in the plane normal to the teeth. Transverse circular pitch, circular pitch in the plane of rotation of the gear, sometimes just called circular pitch. Several other helix parameters can be viewed either in the normal or transverse planes. The subscript n usually indicates the normal worm gear. Nomenclature. Lead distance from any point on a thread to the corresponding point on the next turn of the same thread, measured parallel to the axis. Linear pitch, distance from any point on a thread to the corresponding point on the adjacent thread, measured parallel to the axis. For a single thread worm, lead and linear pitch are the same. Lead angle between a tangent to the helix and a plane perpendicular to the axis. Note that the complement of the helix angle is usually given for helical gears. Pitch diameter, same as described earlier in this list. Note that for a worm it is still measured in a plane perpendicular to the gear axis, not a tilted plane. Subscript W denotes the worm, subscript G denotes the gear. Tooth contact. Nomenclature. Line of contact, path of action, line of action, plane of action, lines of contact, arc of action, length of action, limit diameter, face advance, zone of action, point of contact, any point at which two tooth profiles touch each other. Line of contact, a line or curve along which two tooth surfaces are tangent to each other. Path of action, the locus of successive contact points between a pair of gear teeth during the phase of engagement. For conjugate gear teeth, the path of action passes through the pitch point. It is the trace of the surface of action in the plane of rotation. Line of action, the path of action for involute gears. It is the straight line passing through the pitch point in tangent to both base circles. Surface of action, the imaginary surface in which contact occurs between two engaging tooth surfaces. It is the summation of the paths of action in all sections of the engaging teeth. Plane of action, the surface of action for involute, parallel axis gears with either spur or helical teeth. It is tangent to the base cylinders. Zone of action for involute, parallel axis gears with either spur or helical teeth is the rectangular area in the plane of action bounded by the length of action and the effective face width. Path of contact, the curve on either tooth surface along which theoretical single-point contact occurs during the engagement of gears with crowned tooth surfaces or gears that normally engage with only single-point contact. Length of action, the distance on the line of action through which the point of contact moves during the action of the tooth profile. Arc of action, quart, the arc of the pitch circle through which a tooth profile moves from the beginning to the end of contact with a mating profile. Arc of approach, QA, the arc of the pitch circle through which a tooth profile moves from its beginning of contact until the point of contact arrives at the pitch point. Arc of recess, QR, the arc of the pitch circle through which a tooth profile moves from contact at the pitch point until contact ends. Contact ratio, MC, epsilon, the number of angular pitches through which a tooth surface rotates from the beginning to the end of contact. In a simple way, it can be defined as a measure of the average number of teeth in contact during the period during which a tooth comes and goes out of contact with the mating gear. Transverse contact ratio, MP, epsilon alpha, the contact ratio in a transverse plane. It is the ratio of the angle of action to the angular pitch. For involute gears, it is most directly obtained as the ratio of the length of action to the base pitch. Face contact ratio, MF, epsilon beta, the contact ratio in an axial plane, or the ratio of the face width to the axial pitch. For bevel and hypoid gears, it is the ratio of face advance to circular pitch. Total contact ratio, Mount epsilon gamma, the sum of the transverse contact ratio and the face contact ratio. Modified contact ratio, Mo for bevel gears, the square root of the sum of the squares of the transverse and face contact ratios. Limit diameter on a gear at which the line of action intersects the maximum addendum circle of the mating gear. This is also referred to as the start of active profile, the start of contact, the end of contact, or the end of active profile. Start of active profile, intersection of the limit diameter and the involute profile. Face advance distance on a pitch circle through which a helical or spiral tooth moves from the position at which contact begins at one end of the tooth trace on the pitch surface to the position where contact ceases at the other end. Tooth thickness nomenclature, tooth thickness, thickness relationships, caudal thickness, tooth thickness measurement over pins, span measurement, long and short addendum teeth. Circular thickness, length of arc between the two sides of a gear tooth, on the specified datum circle. Transverse circular thickness in the transverse plane. Normal circular thickness in the normal plane. In a helical gear it may be considered as the length of arc along the normal helix. Axial thickness in helical gears and worms, tooth thickness in an axial cross-section at the standard pitch diameter. Base circular thickness in involute teeth, length of arc on the base circle between the two involute curves forming the profile of a tooth. Normal caudal thickness, length of the cord that subtends a circular thickness arc in the plane normal to the pitch helix. Any convenient measuring diameter may be selected, not necessarily the standard pitch diameter. Caudal addendum height from the top of the tooth to the cord subtending the circular thickness arc. Any convenient measuring diameter may be selected, not necessarily the standard pitch diameter. Profile shift, displacement of the basic rack datum line from the reference cylinder, made non-dimensional by dividing by the normal module. It is used to specify the tooth thickness, often for zero backlash. Rack shift, displacement of the tool datum line from the reference cylinder, made non-dimensional by dividing by the normal module. It is used to specify the tooth thickness. Measurement over pins, measurement of the distance taken over a pin positioned in a tooth space and a reference surface. The reference surface may be the reference axis of the gear, a datum surface, or either one or two pins positioned in the tooth space or spaces opposite the first. This measurement is used to determine tooth thickness. Span measurement of the distance across several teeth in a normal plane, as long as the measuring device has parallel measuring surfaces that contact on an unmodified portion of the involute. The measurement width along a line tangent to the base cylinder. It is used to determine tooth thickness. Modified addendum teeth of engaging gears, one or both of which have non-standard addendum. Full depth teeth in which the working depth equals 2.000 divided by the normal diametral pitch. Stub teeth in which the working depth is less than 2.000 divided by the normal diametral pitch. Equal addendum teeth in which two engaging gears have equal addendums. Long and short addendum teeth in which the addendums of two engaging gears are unequal. Pitch nomenclature. Pitch is the distance between a point on one tooth and the corresponding point on an adjacent tooth. It is a dimension measured along a line or curve in the transverse, normal, or axial directions. The use of the single word pitch without qualification may be ambiguous, and for this reason it is preferable to use specific designations such as transverse circular pitch, normal base pitch, axial pitch, tooth pitch, base pitch relationships. Principal pitches. Circular pitch, arc distance along a specified pitch circle or pitch line between corresponding profiles of adjacent teeth. Transverse circular pitch, PT circular pitch in the transverse plane. Normal circular pitch, P circular pitch in the normal plane, and also the length of the arc along the normal pitch helix between helical teeth or threads. Axial pitch, PX linear pitch in an axial plane and in a pitch surface. In helical gears and worms, axial pitch has the same value at all diameters. In gearing of other types, axial pitch may be confined to the pitch surface and may be a circular measurement. The term axial pitch is preferred to the term linear pitch. The axial pitch of a helical worm and the circular pitch of its worm gear are the same. Normal base pitch (PN, PBN) an involute helical gear is the base pitch in the normal plane. It is the normal distance between parallel helical involute surfaces on the plane of action in the normal plane, or is the length of arc on the normal base helix. It is a constant distance in any helical involute gear. Transverse base pitch (PB, PBT) in an involute gear. The pitch is on the base circle or along the line of action. Corresponding sides of involute gear teeth are parallel curves, and the base pitch is the constant in fundamental distance between them along a common normal in a transverse plane. Diametral pitch (PD) ratio of the number of teeth to the standard pitch diameter in inches. Normal diametral pitch (PND) value of diametral pitch in a normal plane of a helical gear or worm. Angular pitch theta n, tau angle subtended by the circular pitch, usually expressed in radians.